Hello, in today's video, we are going to be moving on to chapter 17. So we will do part of chapter 17 now. Specifically, we are going to cover common ion effect in this video and solubility. And then we will come back to chapter 17 when we talk about acids and bases. So the first thing we have today is the common ion effect. As the name implies, you add an ion that is common to something that is already part of the equilibrium system. And since you are changing one of the ions in the equilibrium system, that will affect the equilibrium. So here's our reaction. We have acetic acid plus water ionizes to make the hydronium ion and the acetate ion. So if we add something like sodium acetate, that would ionize into the sodium ion, which would have no impact whatsoever on the equilibrium, and the acetate ion, which certainly would affect the equilibrium. So if we increased the acetate ion, that would cause the equilibrium to shift to the left, or the reverse reaction would be favored, because if we have too much of the acetate ion, we would need to move away from that. So if we add an ion that is in common, then it will impact that, and the equilibrium would move away from that ion. So again, the common ion effect says that if we add a strong electrolyte, so again, something like sodium acetate in that previous example is a strong electrolyte, meaning that it ionizes fully in solution. So it would add sodium ion, which won't impact the equilibrium at all, and it added the acetate ion, which certainly affected the equilibrium. So then we saw the equilibrium shift away from the acetate ion. So if we have this example here, we have silver chloride ionizing to make the silver ion and the chloride ion. If we add NaCl, so we have water because it's aqueous solution. So if we added NaCl, we would really be adding the sodium ion, which is not going to impact the equilibrium at all, and the chloride ion, which will impact the equilibrium. So if we added NaCl, that would increase the concentration of the chloride ion, which would then cause the reverse reaction to occur. All right, so now we have a calculation with the common ion effect. But first, I want to do the calculation pretending it is just in distilled water and no common ion. So first, we're going to do just in distilled water, no common ion. Then we will do it again, showing the effect of the common ion. So we would start with doing an ice chart. You would have no silver, none of the chromate. We would gain 2x for the silver and x for the chromate. So when we go to write our equilibrium expression, it would be the concentration of the silver ion squared times the concentration of the chromate ion. So then we can plug in our values. Again, we're pretending we're in distilled water right now and we're ignoring the common ion stuff. So our K value is 1.1 times 10 to the negative 12. That's obviously very small, telling us that not many of the ions would exist in solution. So the reverse reaction would be heavily favored, is equal to 2x squared times x. So if we did our algebra on that, that would be 4x squared times x, so 4x cubed. So then in order to figure out the value of x, we would do 1.1 times 10 to the negative 12th divided by 4. That would give us x cubed. So then we would need to take the cube root of that, or to the 1/3 power, in order to find x. And that would have a value of 6.5 times 10 to the negative fifth. So that would be how much chromate we would have in solution. If we were looking for the silver, it would be double that. And the molar solubility would be how much of the silver chromate had dissolved. So that would have the same value of X because they're in a 1-to-1 ratio. So this would tell us how much of the silver chromate had dissolved in solution, how much chromate we had in solution, and double the value for silver in solution. So we see that it's not a very large amount, which makes sense because our K is very small. All right, now what we are going to do is we are going to erase that, and now we are going to plug in our common ion values and see how that affects the equilibrium. All right, so now we are not starting with 0 of both of our ions. Now we have some calcium chromate in there. So our original concentration of the chromate ion is 0.075. Now, this is still going to increase by 2x, and this is still going to increase by x. So our equilibrium values would be 2x for the silver ion and 0.075 plus x for the chromate ion. However, since K is very small, X is going to be very small. Therefore, 0.075 plus X will be essentially equal to 0.075. So even on that previous one that we looked at where it was in distilled water and we didn't have the common ion, our X value was 6.5 times 10 to the negative fifth. So if we added that on to 0.075, it would still, once we rounded it, give us 0.075. So this assumption here is so nice, and this helps save us a lot of math work. Now we can only do this when our K values are very small. So they should be 10 to the negative fifth or smaller in order to make this assumption. And then you do need to acknowledge that you are making this assumption here. Okay, so now we can plug into our K expression, which again is going to be the silver ion squared times the chromate ion. All right, and our value for K is 1.1 times 10 to the negative 12th. Silver is going to be 2x squared. And the chromate ion is going to be 0.075. Again, because even once we add the x to it, it's going to be essentially that. So now we can just do our math. Remember, this is going to be 4x squared, so don't forget about that. So you can, do your math. So 1.1 times 10 to the negative 12th, divide that by 4, divide that by the 0.75. That's going to give you x squared. So that's like 3.67 times 10 to the negative 12th. Then take the square root of that in order to find x. And we get 1.91 times 10 to the negative 6 would be x. So remember when we did this problem previously in distilled water, x had a value of 6.5 times 10 to the negative fifth. So we can see that adding our common ion decreased the solubility of the salt, which makes sense because the reaction shifts backward. So we will have now even less of it dissolving in solution. And with significant figures, we actually only want 2 significant figures. So it would be 1.9 times 10 to the negative 6. So I should not have circled that yet. We just want the 2 significant figures. Now, maybe you're noticing that these K values are so small and that we are not getting many ions in our solution at all. And you might even remember our solubility rules from the beginning of the year. And you might even be thinking, hey, some of these things were on our insoluble list. So we need to talk about that a little bit. So, salts that we classified at the beginning of the year as insoluble, they will dissolve a tiny, tiny, tiny bit in equilibrium. And the amount that they dissolve is going to directly